Good afternoon, guys. I'm just gonna make a quick video on friction. All right, with this we finish chapter 5, and then we will go into week 7, which will be centripetal forces, centripetal acceleration, and applications on circular motion. Newton's laws on circular motion. So friction is just the idea of a body having some sort of force opposite to the motion. So in Newton's second law, we said that the sum of forces is equal to mass times acceleration. But we say that is the sum of forces or the net force because you can easily have a net force going, or sorry, you can have a net force due to a force pushing a body, but then you may have some sort of friction. And there are two types of friction that you need to know. We have the static friction, which is the one that happens when you have a body of mass m and it's not moving, even though you may be trying to move it with a force F. What happens is that because the body has a large enough amount of weight, which happens to be the normal force, then the friction is acting on the floor, on the body, with the floor on there. So this friction depends on, we label it like this, on the normal and a coefficient that in this case, we call it the mu static because it's not moving. So this is called the static friction. And if you look at the slides, they give you a nice explanation with a graph of how we can test this in the lab. You have a force trying to push an object, and then when you reach a limit, which is this value, so if your force is equal to this, that's when the body starts moving with constant speed, because the net force will be 0, no acceleration. And if your force then, or by the way, once the object starts moving, the static friction stops acting, but there is still some sort of friction. That's when you have kinetic friction. So it's a quick summary, I know, but I think it's a good way to just summarize static and kinetic. So static friction, we can say is Fs is normal times μs. And for the kinetic friction, once you move the body with some force, once you do that, the friction acting on this object, so let's say it's now moving with some acceleration, is actually the kinetic friction. Fk, we call it the normal times mu k. So this is normally, or is always less than this. You need more force to start moving an object. Once you move the object, you still have some friction, but it's easy to keep it in motion. So if your force is equal to that, then you can easily say that the sum of forces, or the net force, is equal to, well, in this case, just put F minus normal mu. Okay. Don't be surprised if later on, when we talk about, work, energy, even in this chapter, they will just tell you that coefficient of friction. When they just give you one coefficient, then you just use that one to find the friction between the body and the floor or the surface. So I'm going to do now a few problems of how you do friction. And in fact, let's do the problem similar to the one that you guys have in the Webassign. You have a wall, you have a tension, and then you have a big mass, and you have a small mass here. Let's make this bigger. So you have that this is the wall. This is 10 kilograms. Let's make this 5 kilograms. Always gravity going downwards. And they tell you that there is some friction between the body and the mass. And I'm just going to make it 0.2. So between the masses, they say that mu k is equal to 0.2. All the surfaces. So actually, there's also here mu k equals to 0.2. All right, that's an interesting problem. And on top of that, they give you a force. So here's where you have to find, or you have to do your forces diagram. Let's make the force 15 newtons. So it's crucial to find the normals, because we know that the friction, the general equation for friction, is mu times the norm. For the 10 kilogram, I will draw a picture of the 10 kilogram. It's not to scale here. And is being accelerated due to this force. There is a force of gravity acting due to 5 times 9.8, 49 newtons. And also its own weight. But 49, 98, there is a normal here. Let's call it normal 1. Normal 1 is equal to 49 plus 98. Now, why do I need that? Because using the normal, I can find the friction. There is friction acting here. That friction will be mu times the normal. Right? So that's why it's very crucial that you understand or that you do your forces diagram. 29.4. Perfect. Hey, what? Wait a second though. There is also a body. And between these two bodies, there's friction. So this is incomplete. Let's actually check what's happening with 5 kilograms here. With 5 kilograms, if I do it here, there is the weight acting, right? That's 49. But there is a normal, which is also 49. Let's call it number 2 equals to 49 newtons. There is a tension acting here that is pushing it towards the wall. So when you are pushing this body, this object is going to try to go towards the left because of the tension, right? So then there is a friction, and friction is always opposite to the motion. So guess what? The friction for this guy goes here. And that friction is 49 times 0.2. That will be 9.8. 9.8 newtons. It's friction there. So now, how does that friction affect this body? Well, we have to use Newton's third law. Newton's third law says that whatever action is equal has an equal and opposite reaction here. So if 9.8 is acting like that to 5 on 10 kilograms, will be acting as you will expect logically here. That's 9.8. Now, in real life, it's like if you had a mass over another mass and you are trying to push it. Imagine there was no tension. By inertia, in physics, at this level, we normally say that there is some sort of like frictional force that is making the body slide, and then you move it like that. In this case, you are trying to push it, but there is friction, right? So the friction is making it harder to pull it because there's friction on the ground, but there's also friction between the masses. So this makes perfect sense. In the case of the body as well, because 5 kilograms is trying to be dragged due to the tension here to the left. But because I'm pushing it and there is friction between the masses, the friction is making it try to go to the right. At the end of the day, they are a system. So they have the same acceleration. For 10 kilograms, what's the net force? So we put it here. For the 10 kilogram mass, you have 50 to the right, 29.4, 9.8, so that's 12, 39 point, what? 12, yeah, 39.2. So 50 minus 39.2 equals to 10 times the acceleration. And I believe the problem is also asking you to find the tension on the string. Well, tension minus 9.8 equals to mass times acceleration. Well, let's find the acceleration here. 50 minus 39.2 is 10.8 divided by 10, 1.08. And then tension for the 5 kilogram here right? Tension minus 9.8 equals to 5 times 1.08. So the tension should be strong enough to hold it there. 15.2 newtons. You do it like that, you can get attention. This is a very interesting problem. I basically solved it for you guys, but you could have a problem like that in the exam, on the test on this chapter. There's one more though. Don't close the video. I know that it's a recording because look what I'm gonna do now. Now I'm going to do an inclined plane wave friction. Actually, before we do that, let's show you another example that I always give students. You can have on the floor a body with mass, say, we'll see. But I'm gonna give you a force acting like that. And that's gonna be an angle of 50 frame. This force is of 500 newtons. And I'm gonna give you a mu kinetic of 0.25. And then let's give you a mass of 12 kilograms. Find the acceleration of that mass. Many students, what they do is, first of all, they draw the forces acting here. So that's good. 12 times 9.8. That's the weight, the normal going up. But be careful though. The normal goes up like that, right? But it's not this though. So you leave it like that for now. There is friction here, which is because of that. So you want to draw it here. Just put Fk. And then let's take a look at this force. This force is 500. So I can break it into components. 500 cosine, 500 sine. And you're probably seeing what's going to happen. This is 300 newtons. This is 400 newtons. So what's happening is that there is another vertical force acting on the body. So I can move this vector here. So any vertical force affects the normal. So let's put N here. So that's not this. Okay, let's change some of these values to 50, 40, and this thing. You will see now in a second why it was too much force. 12 kilograms is not a lot. So 12 times 9.8 is 117.6. But there are two forces going on. Normal plus 40 is equal to 117.6. So your normal is actually 77.6 newtons. So what's my friction then? 77.6 times 0.25. I get 19. So this friction here so the net force on the horizontal I have 30 minus 19.4 equals to 12. That will give me 0.88 meters per second square. All right, guys, that's basically another example of how you use friction now. Okay. Let's do an inclined plane now. For the inclined plane, I want to do this example because the normal on the inclined plane can be confusing sometimes. With 60 degrees, let's give you a mass. Let's say, okay. Let's put 5 kilos here, make it simple. Always gravity. And I'm gonna give you a mu of how much. Let's give you 0.2, all right? So let's say that the mu 0.2, dimensionless, okay? It's a coefficient that depends on the surface, right? Can be the floor, sand, the ground, metal, wood. Let's try to change the, well, let's say that, yeah, no, that's fine. And let's actually add that the distance here is of 10 meters. So let's find how long, the initial speed here is 0 meters per second. Let's find how long will it take for the mass to be here. So how long it takes to fall? We need to find the acceleration. As you probably remember from when we did inclined planes on the week 5, week 6, right? This will give you the force of gravity, 5 times 9.8 is 49. But you have the components like that and like this. This is a component of the weight that makes it fall. 49 sine of 60. This one is 49 cosine 60. Which again, there's no other forces acting on this axis. So that's the normal. So I have that my normal is 49 cosine 60. So now I need this because now I can find with this the friction, mu, the friction acting on the body will be like this. The body is falling, the friction acts like that. Always opposite to the motion. My friction will be 49 cosine 60 times mu, which is 0.2. So that will be 49 divided by 2 times 0.2, 4.9. So not a lot, but still. And the force that is making it fall is a magnitude 49 sine 60, that's 49 root 3 divided by 2. So the net force is this one minus 4.9 equals to what? Mass times acceleration. So as you can see, that idea with all these problems is always to be able to find the net force. .5, I get acceleration, 7.5 meters per second square. But that's not the end of the problem. I want to find time. It's free fall, sort of, right? It's initial speed is 0. To find that time, you will do the distance equals to 1/2 acceleration t squared. So time will be 20 divided by 7.5 and the square root 1.63, 1.6 seconds. Friction only happens when you have two bodies or one body interacting with a surface. If you have a body hanging in a pulley like the Atwood machine, you don't have to worry about that. We are not taking into consideration air friction or drag, all right? However, I hope that this is clear. I did a problem with a Webassign. We have basically shown, or I have basically shown you different situations with friction, all right? Again, if you guys have any questions, please feel free to join my office hours, which will be provided most likely. So this is week 6, week 7, so week 6, all right? As I'm doing this video, you guys are probably working on motion on 2 dimensions. So we're getting closer to Newton's laws. I'm finishing Newton's laws with this, but we're gonna continue with applications of circular motion next week. All right, see you guys later, and I hope this is very informative.